Right. It's a pleasure to be back here. It's been many years since I've been on campus. It's hard. It's really unfathomable for me to realize that I probably first stepped, actually not in this building, but the building next door 40 years ago. That makes me feel really old. There are very few people, as you get older in life for the students, there's very few people who you probably interact with now on a regular basis who you will be in touch with 40 years from now. But I guarantee you, if you're a student here, one of those people will be in the alumni office of Stanford University. Because today is Giving Tuesday, and I was even more, so I don't know Donna Lisa, but she was in my graduating class of 1981. She apparently did quite well because she's matching gifts up to $250,000. So I don't think she's an astrophysicist, but anyway, it's a pleasure to be back. I want to talk a bit about the dark energy survey. To motivate that, just remind you, those of you who are not cosmologists, cosmology is extremely simple because the universe on large scales appears homogeneous and isotropic around us. And that means it only has basically a single dynamical degree of freedom, an overall scale factor, which we call A of t, describing the overall expansion or contraction. All other modes would violate this assumption. And this is why I became a cosmologist, because I figured if I could spend my life just trying to find one function of time, it wouldn't be so hard. So the universe is expanding. We've known that since the 1920s, the work of Edwin Hubble and many others. It's natural to ask, is this expansion changing with time? What do we expect? Galaxies are receding away from the Milky Way. The Milky Way is tugging on each of those galaxies. So I would normally expect that if I could measure the recession speed of a galaxy tomorrow, it would be slightly smaller than it is today because of the gravity of the Milky Way is pulling on it. So we expect the universe, the expansion, to be slowing down over time. We expect the second time derivative of this overall scale factor to be negative. So if you go out and measure that, so this is a physicist version of the Hubble diagram, which means that it's easy to understand, but we can't actually measure it. So this is the scale factor of the universe as a function of time. So normalized to units in which its value is 1 today. So we're sitting here at the present epoch, looking back into the past. These different curves are different histories, dynamical histories, for this scale factor as a function of time. All the ones that are colored red are ones in which the universe is slowing down due to the attractive nature of gravity. These ones in blue are ones where it was initially slowing down, but then started accelerating for some reason. So we naturally expected that when we would go back and try to measure this, we would see something like, we would see points lying on one of these red curves. We can measure the scale factor of a given event quite easily through its spectrum, the redshift, and we use standard candles to infer basically a look-back time from how bright different objects appear at different redshifts from us. The surprise, of course, in the late 1990s was that instead of lying on one of these red curves, the supernova points appeared to lie on one of these blue curves. And that was, of course, the discovery of the accelerating universe, which was awarded the Nobel Prize several years ago. So basically, type 1a supernovae that exploded when the universe was about 2/3 of its present size appeared to be about 25% fainter than we expected them to be in a universe that was slowing down. So this was the discovery of cosmic acceleration. So how do we interpret this accelerating universe? Well, you can write down the equation for one of the equations for the dynamics of this scale factor. It's just Einstein's general relativity. Here's Newton's constant, sum over all the constituents in the universe. Rho is the density of each constituent. W is the equation of state parameter for each constituent, the ratio of the pressure to the energy density. And you can immediately see, because of the attractive nature of gravity, there's this minus sign. And so for ordinary sorts of stress energy in the universe, we expect the universe indeed to be slowing down with time. So in order to get a solution which is accelerating, you need to do one of two things. You need to either have some new component in the universe which has a negative equation of state parameter, W less than minus 1/3, so it flips the sign of this sum and dominates over all the other forms of stress energy in the universe. Or you have to say that this equation does not describe the large-scale dynamics of the universe. We have to replace general relativity with some other theory of gravity. So the defining feature of what we now call dark energy is simply that it's a dominating component with an equation of state parameter W less than minus 1/3. A particular example of this is what we call vacuum energy, or the cosmological constant, which is defined to have W exactly equal to minus 1. So we now have this now standard picture of cosmic evolution that's been put in place really over the last 20 years since this discovery. It's a model which involves only 6 parameters. It expands from a hot Big Bang 13.8 gigayears ago. It went through an early epoch of accelerated expansion that we call inflation, which smoothed out the universe and we believe generated large-scale density perturbations from quantum fluctuations. Those grew by gravitational instability to form all the structure we see in the universe today. That picture holds together and agrees with all observations if the universe is made of dark matter, 25% of what we call cold, that is non-relativistic dark matter, and the other 5% is baryons, and the other 70% is a cosmological constant dark energy, which is causing the universe to undergo a second phase of cosmic acceleration that started several billion years ago. This picture is consistent with all the data that we have today. So nevertheless, we want to, from this discovery of cosmic acceleration, the lambda CDM model, we still want to understand the physics underlying this model. What's the physical cause of cosmic acceleration? Is it more fundamentally dark energy, or do we have to replace Einstein's theory of general relativity? If it is dark energy, is it simply the cosmological constant, the energy of empty space, or is it something else, perhaps something dynamical? One way among a number to quantify that question is to ask what is this equation of state parameter for the dark energy, and how and does it evolve? The reason we focus on this equation of state parameter is because it determines how the density of dark energy changes with time. So this is log of energy density versus log of the scale factor, or redshift. So we have the familiar forms of radiation, relativistic particles, matter, non-relativistic particles. Those dominated, radiation dominated at early times, then we had a matter-dominated epoch, and then several billion years ago, the universe, we believe, became dark energy dominated. And this equation of state parameter determines the time evolution of this dark energy density just through the equation of conservation of energy momentum. Okay, so what are some of the possibilities? I'll point to just one. Our simplest picture of cosmic inflation, the primordial epoch of cosmic acceleration, is that it's driven by a simple evolving semi-classical scalar field, a ball rolling down a hill in a potential. And we know that if the ball rolls slowly enough, that is, if the potential is relatively flat, the kinetic energy of the scalar field is going to be small compared to the potential energy. Here's the expressions for the energy density and pressure of a scalar, homogeneous classical scalar field. So you can see if the kinetic energy terms are small, then the equation of state of this effective fluid, or this scalar field fluid, is just going to be that the pressure is minus the energy density. That is, W is minus 1. It won't be exactly minus 1. It'll differ from it slightly since this field is dynamical. So it could be that this same kind of mechanism is driving the current accelerated expansion of the universe. It would require a scalar field with an incredibly small mass, but it's in principle possible. So we want to determine this sort of physics. What's causing this accelerated expansion? Is it dark energy, modified gravity? Is it perhaps a new dynamical degree of freedom? And the way we do this in the dark energy survey and other surveys is to probe the expansion of the universe and the growth of structure. So we have basically two kinds of probes that we can apply. One is the expansion history, so we measure Effectively, we measure distance versus redshift, that is the Hubble diagram, or in some cases we can measure the expansion rate itself as a function of redshift. And so here are plots of distance versus redshift as I vary this equation of state parameter W. So you can see if I can measure this distance versus redshift precisely enough, I can constrain the dark energy equation of state. And this is the method that the supernovae use. The second technique, a more recent technique, is to look at the growth of structure in the universe. So this is looking at the amplitude of fluctuations or of clumpiness of the mass in the universe as a function of redshift or as a function of scale factor going towards 1 to the right for two different values of this equation of state parameter. And so this equation of state parameter, since it alters the expansion rate history, also therefore through general relativity alters the growth rate of perturbations. So in principle, if we can measure the clumpiness of the mass distribution as a function of redshift or look back time and see which of these curves the amplitude lies on, that again gives us an independent handle on the properties of dark energy. And what we want to do going forward is really employ both of these kinds of probes, both geometric expansion history probes and the growth of structure, because they give us complementary information. And in particular, if the right model is general relativity plus dark energy, there's a consistency relation between these predictions. Whereas if instead I have a modified gravity model, I move away from general relativity, then generally the general relativity consistency relation between these two kinds of measurements can be broken. So if we can measure both expansion history and growth of structure at the percent level, we can test general relativity in a fundamental way. So I just want to illustrate that here. This is some simulations done by Riza Wexler here and her group. These are formation of structure in a lambda CDM model, where the initial level of perturbations gives rise to a cosmic microwave background anisotropy that's the same in both models. But the other cosmological parameters differ between these, leading to different growth rates of structure and therefore different amplitudes of clumpiness in the present universe today. So this is an extreme example where we varied the parameters a lot, but it gives you a qualitative sense of what we're trying to do quantitatively. If we can measure this clumpiness of the mass distribution, that will give us this extra handle on cosmic expansion history. So there are four primary ways we have of getting at combinations of expansion history and growth of structure. One of them is to just look at the abundance of clusters of galaxies. Clusters are stand-ins, they're proxies for massive dark halos. So people here like Steve Allen and others have really been leaders of this kind of work. And basically, this is a plot of the expected number of dark matter halos above some mass threshold as a function of redshift in some solid angle of a survey as a function of the redshift to which that survey reaches for three different values of this equation of state parameter W, holding all the other cosmological parameters fixed. So at low redshift, the curves differ from each other because of expansion history, this geometric factor here. At high redshift, the curves differ in the opposite way, and that's just given by the differences in the growth rate of structure as I vary this equation of state parameter. And so this is a very promising technique. You essentially go out, you do a survey, you count the number of massive clusters you find, and then just see which of these curves that lies along as a function of redshift. The challenge, of course, is that what we can actually observe are clusters of galaxies. They are not massive dark halos. They are proxies for dark matter halos. And there's some probabilistic relationship between the mass of a dark halo in which the cluster sits and whatever observable about that cluster we can actually measure. Say the number of red galaxies it contains, or its X-ray flux, or the Sunyaev-Zodowicz flux decrement from the microwave background. Each of these is a different observable which has some relationship to the underlying mass of that cluster, and it's our knowledge of that relationship will determine how accurate of a cosmological probe this will turn out to be. And there's a lot of work that's being done here on that technique. Second technique is weak gravitational lensing. So this is the fact that light from distant galaxies, as it travels to us, doesn't go in straight lines, but it gets bent by the inhomogeneous foreground distribution of dark matter, clumps of dark matter halos. That leads to a shearing of the images of these distant galaxies. And those shears, those induced ellipticities, are correlated along nearby lines of sight. So by measuring the correlation function of the cosmic shear, which is a very tiny effect, we're talking about just a 1% distortion of the shapes of galaxies, that gives us a second handle on both expansion history, because this is a geometric effect, these distances, as well as the growth of structure, which is determining the clumpiness of this foreground lensing mass distribution. And so this is just an illustration here. This is the angular power spectrum of that cosmic shear as a function of angular multipole on the sky. And this is just a theory prediction for 3 different slices of redshift for 2 different values of this equation of state parameter W. And the point is that the amplitude and to some degree the shape of this power spectrum of the cosmic shear depends on this parameter. Third technique is called Baryon acoustic oscillations. This is basically the same physics that leads to the hot and cold spots that you see in the famous maps of the cosmic microwave background. That leads to a periodic ringing in the angular power spectrum of galaxies in different redshift bins. And again, that ringing, the phasing of that ringing is sensitive to the equation of state of dark energy as well. So if we can measure these rather subtle spatial frequencies, we can also constrain the properties of dark matter. Fourth technique is the tried and true method, type 1a supernovae. These are standardizable candles. We measure their distance versus redshift. And the plot here from Dan Skolnick is just showing you theory predictions as I vary. Again, these are different cosmological parameters, including the equation of state. And so we're looking for rather tiny differences in the distance versus redshift for type 1a supernovae to try to measure the equation of state parameter to high precision. So the dark energy survey was designed to bring these 4 methods together into a single experiment by carrying out 2 interleaved multi-band surveys. A wide area survey that covers 5,000 square degrees, that's 1/8 of the entire sky, in 5 optical passbands, GRIZY, to a depth of 24th magnitude. That means we'll measure properties of about 300 million galaxies over that area. And then we interleave that every week or so. We revisit 27 square degrees of sky to discover and measure light curves for several thousand of these supernovae. To carry out such a survey, we had to build a new camera, a new instrument, so we did. We built the dark energy camera, shown here, mounted on this Blanco 4-meter telescope. It's high in the Chilean Andes at the Cerro Tololo Inter-American Observatory. This is a US facility funded by the National Science Foundation, operated by the National Optical Astronomy Observatory. So CTIO is a user facility. We built this camera for the astronomy community, and we get to use it roughly 1/3 of the time for 5 years. Our survey started in August of 2013. Our seasons go from August to February. That's when this 5,000 square degree region is up at night. We observe 105 equivalent nights per year for each of those seasons. And I want to acknowledge the support of both the Department of Energy and the National Science Foundation in making this project possible. The other thing you need to do for this kind of project is you need to build a big collaboration of people to build these kinds of instruments, to build the software, to run it, operate it, and to analyze the data. And so we now have a collaboration that's roughly 400 scientists from 26 institutions in 7 countries, including an active group here at CAIPAC. We get together every 6 months or so for collaboration meetings. This is one we had back in June. It's a very photogenic group of people. We typically have about 175 people get together for a week. I realized the best thing about having a collaboration meeting is it makes people do work before the meeting. So they're extremely useful. Since May of 2014, where our first science paper was submitted, we've submitted over 140 papers to referee journals, and most of them have been published. I just want to recognize here the group. I don't have time to call out the individual contributions of everyone here, but both senior and early career scientists here, this is, I think, summed over the life of the project pretty much. It's a very impressive group. It's been extremely active, playing key roles in a variety of points of the survey, from construction through operations to leadership in science analysis. So it's been a real vital part of the collaboration. Here's the actual guts of the project. This is the focal plane of the dark energy camera, 570 million pixels, covering 3 square degrees on the sky. It uses these deep, fully depleted CCDs that were developed by Lawrence Berkeley Lab. So they're much thicker than conventional astronomical CCDs, which gives them excellent quantum sensitivity, particularly in the red parts of the visible spectrum. And since we're trying to do a deep survey, that's quite important. We observe through these 5 filters, G, R, I, Z, and Y, and you can see having this extra efficiency, particularly in the 3 reddest passbands, gives us a big boost in survey efficiency compared to if we had used conventional thin CCDs. And the camera has worked remarkably well over 5 years. It has a 5-element optical corrector system of lenses to give us excellent image quality over the full 3 square degree field of view. This is my colleague Steve Kent doing a precision measurement of the diameter of the largest lens, checking that it was exactly 0.9 meters. We have obviously very small tolerances in the design of the whole project. This is that same lens after it's been polished and buffed and waxed, and here it is installed on the corrector before it goes on the telescope. And this is just another view of the camera. So this whole thing is the dark energy camera. The actual focal plane is up here, embedded in a bunch of electronics. Actually, it's right here. This is a filter and shutter system. The lenses are inside this black barrel, and the whole thing looks down at the primary mirror of this 4-meter diameter mirror of the Blanco telescope. I want to mention these little things here. That's a hexapod system which can piston the focal plane relative to the primary mirror to give us, to improve the focus and also the alignment of the system. And Aaron Rudman here did a lot of work helping us program this and interpret the images in order to get the best control of the optical system using this hexapod system. Here's what a raw image looks like. So you can see each of these 2K by 4K CCDs. Since the start of the project, 2 of the CCDs died. One of them died very early. The other died about a year later. Actually, one of them mysteriously was resurrected last December. We don't know why, but it still works. And so overall, the system has been working very well and quite reliably. And it gives us beautiful images like this happens to be a nearby galaxy. Nice pictures of clusters. Of course, we're not really interested in these very bright nearby things. We're much more interested in these very tiny blobs, these more distant galaxies. Okay, an important thing in being able to analyze these data is calibrating them. And again, I just want to call out some of the very key work that's been done here, particularly led by Dave Burke and Eli Rykoff, in calibrating the photometry. So that when we say that we've measured the flux from this particular star or galaxy, we know that with very high precision. And so they've developed this new method for global calibration, which basically implies forward modeling of the instrument and the time-dependent spatially varying atmosphere, includes chromatic corrections for the fact that different kinds of objects have, in fact, different spectral energy distributions. And at the end of the day, it's really achieved a remarkable precision on our first 3 years of data of about 0.5%, which is really fantastic and really directly feeds into the kind of measurements we can make. So this is the survey footprint on the sky. It's a funny shaped region covering 5,000 square degrees. The region down here, about half of the survey area, is designed to completely overlap with another survey being done of the cosmic microwave background by the South Pole Telescope. That's really why we started the project. And then the region up here called Stripe 82 is the South Celestial Equator. And we overlapped this region because it overlaps the Sloan Digital Sky Survey. We could cross-calibrate with it. And also this region of the sky is accessible to northern telescopes. So there's a lot of ancillary data over this portion of the sky as well. And then this region in the middle just connects those two and gives us more area. And these white little dots are the supernova fields. There's 10 of those, they're each about 3 square degrees. These are the fields that we revisit basically once every 6 or 7 nights. So our goal over 5 years is to cover this entire footprint with 900 seconds of cumulative exposure in each of the GR and IZ filters, 450 seconds in the Y filters. And we simply build up depth over time. This is just showing you the area covered by the South Pole Telescope. Let me play this briefly. So this just shows you another view of the footprint, and it shows you for the first 3 years or so how we actually tiled the sky with exposures. So basically each time one of those is going off, that's one exposure we took, and they're sequentially with how we actually carried out the survey. So the first year of the survey we focused on this region. In the second year we focused on this connector region between the South Pole Telescope and Stripe 82. And then in the third year we basically covered the whole thing. And that's what we're doing in the fourth and the fifth years as well. And now it's just going to zoom in to give you some sense of sort of dynamic scale. Or dynamic range, excuse me. So now you can finally start to resolve individual galaxies. So a very large range of scales that's probed in this kind of survey. Okay. So this is what we had covered after the first year. As I mentioned, we focused on this South Pole Telescope region and a bit on the Stripe 82 region. This data is the basis for the year 1 results that we published in August that I'm going to be talking about. As of a couple nights ago, this is where we had gotten to. So basically a tiling is 1 exposure and 1 filter. And so if we've covered, so this dark blue regions here means that basically in the western part of the footprint, we've done 9 tilings in each of the filters, right? G, R, I, Z. We've done 8 in the Y band for technical reasons. And our goal is at the end of 5 years for this whole thing to be pink, to have covered 10 tilings. That would be the 900 seconds of exposure. We're not going to quite get there, so we're going to do an extension, another half season late next year to fill in the full 10 tiling 900 second survey. All right, so now let me talk about the year 1 results that we released in August. And what we did is what we call 3x2 analysis, 3 different measurements of 2-point correlation functions. One of them was galaxy clustering, measuring the autocorrelation of positions of about 600,000 luminous red galaxies in 5 redshift bins. Second is cosmic shear, weak lensing, correlating the shears of about 26 million source galaxies in 4 redshift bins. And then combining these two, measuring the shears of source galaxies correlated with the positions of foreground luminous red galaxies, again in those redshift bins. We did a fully blind analysis so that we wouldn't be subject to confirmation bias. We developed a number of new and improved analysis techniques that enabled us to really wring a tremendous amount of information out of these data. And we basically released 10 papers on the archive on August 3rd, had a nice press release, etc. Got some nice press coverage. Most of it was pretty good, not all of it. I don't think that the Department of Energy really likes us to be associated with spelling doom for humanity, but I don't know what the express is, but most of the coverage was good and accurate. I'm really resisting saying something about fake news, so I'm just going to go on. Okay, so just a little bit more about these galaxy samples. So in the upper left is the spatial distribution of those 600,000 luminous red galaxies. We picked these because we can measure their photometric redshifts very precisely. I'll talk a little bit more about that in a minute. And these, we measured the clustering of them, and these were the lenses for the galaxy-galaxy lens measurement. And then this is the distribution of the 26 million source galaxies, generally at higher redshift. And this covers 1,800 square degrees. After we make analysis cuts, it was about 1,300. So again, it's only a small fraction of the area that we will eventually cover. I mentioned photometric redshift. So basically, to interpret these measurements, we need to know something about how far away these galaxies are, both the ones we're measuring the clustering for and the ones whose shapes we're measuring. And so we don't have spectrographs. We can't measure the redshifts precisely, but we measure the flux in several different filters. And by comparing the fluxes in different filters, you can see here, this is the spectrum of an elliptical galaxy at redshift 0, 1/2, and 1. And you can clearly see that as it moves out in redshift, the relative flux in the different filters that we observe through is going to change. That is, the colors will change, i.e. it will get redder and redder as it goes to higher and higher redshift. So the trick of photometric redshifts is to train or have some empirical basis for having a probabilistic relationship between measuring the fluxes or colors of an object and inferring its redshift in some probabilistic sense. We can either do this in a machine learning way by having a sample of galaxies whose redshifts we do measure spectroscopically and training this relation, or we can just say, I know what the spectrum of a galaxy looks like. I can redshift it as I'm doing here and calculate what its fluxes or colors should be. And both techniques are used. The real challenge for this approach is that the training sets we have with spectroscopic samples are not complete to the depth that we are doing this photometric survey. That's why we're doing a photometric survey, because doing imaging is cheap and fast. Spectroscopy is expensive and slow. And imaging always goes deeper than spectroscopy for the equivalent amount of resources. And so this is the challenge to this technique. It's a problem for DS, where we're going to 24th magnitude. It's going to be an even greater problem and challenge for future projects like LSST, which are going a couple of magnitudes even fainter yet, where we have even less existing spectroscopic samples. So anyway, so that's the issue of photometric redshifts. So what we do is you have some estimator for the photometric redshift of a galaxy, and we use that to place galaxies in bins of photometric redshift. So the upper panel here is showing you 5 bins, redshift bins for those red magic galaxies, those luminous red galaxies. And then the solid curves are showing you the actual true redshift distribution for the galaxies that we've put into these bins, and it's pretty close. That's because these red galaxies were selected to have very small errors in their photometric redshifts. Essentially, red galaxies, all look pretty much like this. And once you know what its intrinsic spectrum looks like, you can confidently go from fluxes to estimating, inferring the redshift. So that's why we chose that sample. So that works quite well. But then we have these millions of galaxies for which we want to measure the shears. We want to know how far away they are too. So we put them into 4 redshift bins here. And then through independent techniques, we calculate what their actual true redshift distributions are. And you can see they don't match up very well. So look at this highest redshift bin. we said, okay, we think all those galaxies are in here, but in fact, this is their true redshift distribution. Doesn't look very much like this bin. That's not a problem as long as you know that the true distribution looks like this. I don't really care what bin I was trying to put it in, as long as I can, at the end of the day, infer this true N of Z, or redshift distribution. And so the whole, much of our analysis of this data went into inferring the true redshift distribution of galaxies in these photo Z bins. I'm not going to go into the details of how we did it. We basically had independent methods which fortunately agreed with each other, and that gave us confidence that we in fact did have a good handle on the true redshift distributions of these galaxies. I will say one of these methods involved cross-correlating these source galaxies with the red galaxies whose redshifts we knew rather precisely. This angular cross-correlation technique, or redshift clustering as it's called, is an increasingly important tool in this toolkit for validating photometric redshifts and calibrating them. And I want to call out the work of Chris Davis here, among others, who really pushed this analysis forward for year one. The other thing you have to worry about is all sorts of systematic errors. For example, we're trying to measure the spatial clustering of these red galaxies. We have to take into account the fact that in this first year of data, the observing conditions varied with spatial position over the survey footprint. So for example, this is variation in the air mass, how much atmosphere we were looking through when we looked at a particular part of the sky. This is how good the seeing was on a particular, this is how deep we got, this is how bright the sky was. Each of these things in principle can imprint a spatial pattern on your ability to detect a galaxy to a given flux level, and therefore can induce fake density fluctuations, which you have to model and remove in order to get the true signal. So this is the actual result once you've corrected for those systematics. This is the angular correlation function of those red magic galaxies in 5 different redshift bins, from low redshift to high redshift. This is actually theta times the angular correlation function. And then you can also cross-correlate those galaxies in different redshift bins with each other. The ones that are in adjacent redshift bins will have some non-zero cross-correlation because, as you can see here, there's some overlap, right, of the galaxies in this bin with galaxies in this bin in redshift. So there will be a non-zero correlation function between them. But as I move further and further, move the redshift bins away from each other, then there's no overlap, and we expect 0 correlations. And I should say these curves are best fit models using this lambda cold dark matter cosmology. This is the expression for the cosmic shear. So basically, this is what we measure, the cosmic shear angular two-point function in bins of redshift. It's an integral over the power spectrum of the convergence, or the shear, which is itself an integral over the matter power spectrum with some weighting function. And the reason I'm showing you this is just to point out that this weighting functions depend on this redshift distribution. So we don't care about the photometric redshift of any individual galaxy as long as I can infer this redshift distribution. So that's why we were focusing on this. So take a picture of this in your mind. Put in what you all know what the nonlinear power spectrum of lambda CDM looks like. So you can do this integral in your head. And I'm sure you'll agree that at the end it will look something like this. So this is theta times the correlation function. There's actually, since shear is a 2D vector, there's 2 of them, a psi plus and a psi minus. So again, the points are our measurements from the year 1 data. The curves are the best fit lambda cold dark matter models. And they fit quite well. And the errors are consistent with what they should be. I'm going to skip over that. The third of these 2-point functions we measure is galaxy-galaxy lensing. So it's the correlation of the shear of a source galaxy with the position of a foreground red magic lens galaxy. So again, you can do this integral in your head to estimate what that tangential shear should look like. And then you go out and do the measurements in bins of redshift of both the source galaxies and the lens galaxies. And then again, the curves are the best fit lambda CDM model, fit to all of these data, and fits quite well. So now we want to combine all that together and constrain cosmological parameters. We have to use the fact that when we make these kinds of measurements, particularly in real space, these data points are highly correlated with each other. So there's a off-diagonal covariance matrix between points in different angular bins. There's also a covariance between the measurements in different redshift slices. Moreover, there's a covariance between this measurement and the measurement of the angular clustering two-point function of the red magic galaxies themselves. So that means that we end up with a quite complicated, I think it's 467 by 467 element covariance matrix, which we analyze using, which we estimate using a variety of theoretical techniques. This was work led by Elizabeth Krauss, who was a postdoc here. And this is important in being able to turn those measurements into inference about cosmological parameters. So this is what you end up with when you put all that together. And I'm not yet going to be showing dark energy constraints. This is now constraining the amplitude of clustering. So a particular quantity called S8, which is basically just one measure of the large-scale clumpiness of the mass distribution of the universe. And it's a number that should be of order unity. And on the x-axis is omega matter, the density of cold dark matter plus baryons in the universe. And these are the results from those three different combinations. So green is the cosmic shear, so it's the shears of the source galaxies. And red is when we combine the galaxy-galaxy lensing with the clustering of the red galaxy, so we do those together. And then the blue is the combination of those two together. So this is our 3x2 measurement with the tightest error bars. Right, let me move on. So naturally the question is, this is a measurement of, in the context of this lambda CDM model, how does it compare to other measurements, for example, from the cosmic microwave background? So this is the famous map of the CMB temperature from the Planck satellite. You can measure the angular correlation function, or the angular power spectrum rather, of the temperature in the same way we were doing it for DES. And here's again the best fit lambda CDM model. This is from the Planck results from 2015. So it's a very impressive measurement with very tiny error bars. However, they only measure one or two of these, where we get to measure this in many, we're measuring 3 different two-point functions in a whole bunch of redshift bins. So even though any one of our measurements is lower signal to noise than this, we have a lot of them. So we can put them together on the same plot. And so this is the Planck results, again, amplitude of clustering, S8 versus omega matter. And these are our 3x2 correlations. And the first thing to notice is that the size of our error ellipse or error blob is comparable to the size of the Planck error blob. And I think that's important because for many years, the CMB has been kind of the gold standard for cosmological precision. And I think we're now seeing that with these kinds of very large surveys, they are now approaching the precision, at least for certain interesting cosmological parameters, approaching the precision of that of the CMB. And it's quite remarkable that these things are actually anywhere near each other, because this is inferred from looking at temperature perturbations when the universe was 380,000 years old, before any structure had formed. This is looking at the universe 10 billion years later, a lot of nonlinear structure, and the fact that these agree in this simple, to within this precision, within this simple 6-parameter model, I think is quite striking. Now they do disagree at a little more than 1 sigma, but we decided before unblinding that we would use a certain Bayesian evidence ratio to determine if they were consistent or not, and this passed our consistency check. And so that means we can combine these to get combined constraints, which naturally live somewhere in the middle. Whether these two things are in fact consistent will be answered by us and by other future surveys. So we will shortly analyze much more of our data, and we will use additional probes. I haven't used clusters or supernovae, so it's like we have 4 hands, but we've been fighting with 2 of them behind our back so far. So this error bar is definitely going to shrink quite a lot, both with more probes and more area. And we'll see if it shrinks around here and becomes inconsistent with Planck, or if it shrinks around here, where we'll have a consistent model. Okay, let me skip that. I did want to mention we did constrain W in a simple model where we hold this parameter W fixed. In principle, it can vary in time. So if we add 1 parameter to this lambda CDM model, instead of fixing W to be -1, we let it be a free constant parameter. We can do the same constraints, combining the DS data, combining Planck, combining other sorts of measurements, so BAO measurements from the Sloan survey, and previous supernova measurements from the joint light curve analysis team. And at the end of the day, we get an interesting number for W of -1.00 with an error of about 4 to 5%. And I could have shown a couple of more significant figures, and amusingly, they would have been 0 as well. But you shouldn't read anything into this. The real number here of interest is this 4 to 5%. And we haven't yet done the interesting test, which is to allow W to be a function of time. And so I don't yet know whether that will remain the central value when we do that. I want to say a little bit about H0. People have spent careers trying to measure the present expansion rate of the universe. Our data don't really constrain H0 directly, but what we do constrain is omega matter. And we can combine that with Planck, and that basically shifts the central value of Planck upward by about a little more than a sigma on the Planck error bars. Shifts it towards the low redshift distance ladder estimates of H0, but doesn't reconcile the difference between those. We've also done a different analysis where we forget about Planck and just take our measurement of omega matter, combine it with BAO and Big Bang nucleosynthesis constraints on omega baryon to get a new independent measurement of H0 that's independent both of the standard, the distance ladder measurements and the Planck CMB measurements. When we do that, we get a value of about 67 with an error of about plus or minus 1 kilometers per second per megaparsec. Okay, I just want to mention another kind of measurement that can be done with this, and I think that we will want to do increasingly. This was led by Daniel Gruen, who's a postdoc here in KaiPak. So this is doing that same kind of galaxy-galaxy lensing, but now instead of measuring the tangential shear stacked around each of these red magic galaxies, he instead defines underdense and overdense lines of sight based on the distribution of these red magic galaxies. And then in quintiles of that density, measures the tangential shear around those lines of sight. And what you find is that an expected correlation between the amplitude and scale dependence of that tangential shear with the under or over density of those lines of sight. This is an interesting measurement in part because it's sensitive not just to 2-point statistics, but to higher order moments of the density field, which carries independent information about cosmological parameters. Another thing we can do with this data is actually make a map of the projected mass distribution using weak lensing. So this was work led by Chi-Wei Chang, who was actually a graduate student here several years ago. So this is a map of overdense in red and underdense regions in blue, projected mass density inferred from those same cosmic shear measurements. And it gives you a nice visualization of the distribution of large-scale structure. Some of these large-scale structures that your eye thinks extend over, this is about a few hundred million light years across here, actually more than that. Some of these, you might wonder if these are real 3-dimensional structures. Some of them will be, others will just be chance projections of a bunch of structures, mass concentrations at different redshifts that just happen to lie near each other on the sky. Okay, let me skip that. I want to say a little bit about supernova. We haven't published our supernova results yet, but that's to come. Our first supernova results, hopefully at the January AAS. We've now amassed very nice multi-band light curves for a couple thousand of these type 1a supernovae, including ones out to a redshifts of order unity, which is pretty impressive to be able to do from the ground. Again, this is thanks to these very thick CCDs, which have excellent sensitivity in the Z-band. We've been following up many of these with a 4-meter telescope in Australia, which magically has this exact same field of view as our camera. So they can do multi-fiber spectroscopy of supernovae and also of host galaxies of supernovae. And so this is very useful for using those objects for cosmology. This is a simulated Hubble diagram of our final supernova sample. One thing to mention is that DES and LSST are going to find thousands, LSST tens to hundreds of thousands of these supernovae, but we don't have the resources to measure spectra for all of those supernovae while they are bright. A type 1a supernova is a supernova that has a particular set of spectral features. So in the future, what we mean by a type 1a supernova is going to change. It will not be this thing has a particular spectral feature. It will mean we think it has that spectral feature based on the light curve that we've measured in multiple passbands for that object. That works quite well, but it doesn't work perfectly. And in some cases, there will be non-1a supernovae, which will pass your cuts, will look to a photometric classifier like a type 1a supernova, but if you could have gone out and measured its spectrum, you would find that it was not, in fact, a type 1a supernova. So the success of this enterprise is going to, will sink or swim on how well we can constrain this contamination level and model it. We think it's under control, but this is still very much new territory. So our first results are going to be based on just a spectroscopically confirmed subsample of these. In the interest of time, I'm going to skip a few other topics and just finish with a couple of other ones. So a sort of a side note is, so we designed this survey to do cosmology, but darn it, we have people who aren't all interested in dark energy, including people like Keith Bechtel and Alex Derlika-Wagner, who are both students here, who got very interested in using our data to search for new, very ultra-faint dwarf galaxies in the backyard of the Milky Way. And as of today, they've found about 17 of these. And these are interesting for a number of reasons, for learning about structure formation. They're also interesting because these are very dark matter rich systems. They're in our cosmic backyard. So if are dark matter WIMPs in the cores of those dark matter dominated dwarf galaxies, they will be annihilating and give rise to a gamma ray signal, which in principle could be seen by Fermi-Lat. So we joined forces with the Fermi-Lat team to look at the gamma ray signal or lack thereof in the directions of all these new ultra-faint dwarf galaxies. And we've been able to use that to place new constraints on the annihilation cross-section of dark matter into BB bar and taus as a function of dark matter mass. So those constraints are shown here. And interestingly, these are the preferred regions if you have a dark matter, if you want a WIMP annihilation to be the cause of this galactic center excess that's been inferred. So you can see that the constraints from annihilation in these dwarf galaxies is just right in the range of sort of on the edge of perhaps ruling out those kinds of models. And so we want to find more of these and see if we can push these limits down. I want to spend the last couple of minutes talking about sort of something which was really a side issue for us, which sort of broke out in a very public way in the last couple months. And this is using the dark energy survey to follow up gravitational wave triggers. So as you know, LIGO has now been operating for a couple of years, and they put out triggers to a subset of the community saying, gee, we think we've seen an event, why don't you go and look, see if you see any optical light from it. The first 4 events they found were binary black hole mergers. We and others looked, didn't see anything. We didn't expect to see anything. But a binary neutron star merger is expected to have an electromagnetic counterpart called a kilonova. Our interest in this is that kilonovae have been proposed as a new way to measure the expansion rate, the H0, because the gravitational wave signal gives you a distance to that event. If you can identify an optical counterpart and thereby measure the redshift of the host galaxy, then you have a new Hubble diagram to play with. And the hope is that with a few tens of events, you could get a competitive measurement of H0 from this technique. Now the problem is that LIGO cannot tell very well where a particular gravitational wave event came from. So their localization region of any of their events on the sky is tens to hundreds, some cases many hundreds of square degrees. Well, our camera has a big field of view, 3 square degrees. It's on a largest telescope, so we can efficiently cover tens to hundreds of square degrees quite deeply rather quickly. And so we devised a program to basically interrupt our survey for a small fraction of time to do this kind of follow-up. And this is particularly useful because we're in the months between August and February, we have someone there on the telescope almost every night. We're on about 3 out of every 4 nights during this period. So if a trigger comes in, more than likely we will be on the telescope that night. So this is the localization regions for the first LIGO events. Things improved dramatically when Virgo turned on in August, and their localization regions went from these very large, many hundreds of square degrees regions to tens of square degrees for these 2 events in August. So our plan is basically once we get an alert from LIGO, they say it's roughly here. We tile that region with exposures of DCAM. This is just a simulation of some kind of event. This is our footprint of our survey. And then this blue region is showing as a function of time over the course of a night what part of the sky is visible. And so basically as this field rises, we can tile it and then sequentially go through it over the course of typically a couple of hours. We then process those data through a difference imaging pipeline and look for any kind of new transient. So on August 17th, LIGO put out their first binary neutron star trigger. It was in this part of the sky. This is our survey footprint. And basically this is the accessible part of the sky that we had to work with from CTIO at the beginning of the night of August 17th. So it was basically, again, this is just a different version of that. This is emission from the Milky Way. So this is the LIGO region. The red is showing you the tiling strategy we adopted to cover that. And basically this is the part of the sky that's above the horizon at sunset on August 18th in Chile. And basically you can see that this object was very close to the sun. So it was basically only visible for the first hour and a half after sunset, and then it just sunk below the horizon. So that means we had to get on it right at the beginning of the night. So we did so as soon as it was dark enough to start taking astronomical exposures. We did so. It was about 10.5 hours after the alert that we received. 30-second exposures in the I and Z bands, and we covered 70 square degrees. And we basically had teams of people eyeballing the images. At 9:05 p.m. local time, we did this exposure here. And then our colleague, Ryan Chornock, who was among the people looking at the exposure, sent this email. Now, I was actually on vacation with my daughters when this happened. And you've got your phone out, you're at the beach or something, you're sort of checking emails. And usually when I get an email that just says, holy shit, I usually like, oh man, I really don't want to read this. But in this case, I read a little bit further and I was like, oh wow, gee, this is kind of exciting. So it was the good kind of holy shit. And so this is what Ryan saw. Basically, he saw this thing. And this is an image we took 2 weeks later when it had faded. So this is the optical counterpart to that gravitational wave event. The little known secret is, the way to find transients in astronomy is you just look for the hash marks, and they always point to the things. Sometimes they're arrows. It depends on the telescope. Some telescopes come with arrows pointing to them, but our camera comes with hash marks, so it's very useful. And basically, we were one of a number of groups that were looking for this thing that night and who independently discovered it. And this pair of images actually appeared sometime last month in New York Times. This is a light curve, a multiband light curve that we measured with the dark energy camera of this event. Faded quite rapidly. It was initially quite blue. The blue light faded quite rapidly, and it turned increasingly redder as it faded. I'm not going to go into the details of kilonovae, but again, we were interested in this object for measuring H0, and again, this is just a plot showing you this sort of current discrepancy between C and B measurements of H0 down around 67 and the local distance ladder measurements with values of around 73. And so this is the measurement inferred from LIGO plus us and the other electromagnetic groups. So again, the green is the Planck measurements. The orange is, so this is Adam Rees et al., the shoes measurement using the local distance ladder. And of course, the LIGO measurement peaks beautifully right in between them at 70. But of course, with quite large errors from just one single measurement. Interesting thing is that a lot of this, the contribution to the width of this curve comes from the uncertainty in the inclination angle between the orbital plane of the merger and our viewing direction. So we also did another analysis where we used the electromagnetic follow-up to get better constraints on that inclination angle. And when you do that, that actually pushes up the best fit value to even higher values of H0 using that prior. But again, this is, I think, just a proof of principle. And once we have tens of such events, it'll be quite interesting to see where it comes in. Okay, let me skip this. If anyone's interested, I can talk about planets. So where are we going? So I said we're now analyzing the first 3 years of data that covers the full 5,000 square feet footprint. We're planning to do that in the next year, and then we will analyze the full 5-year survey. This is our prediction for how well we'll do in this two-dimensional parameter space of an evolving dark energy model compared to where sort of the world constraints were as of a few months ago. So still lots of room for improvement. This is using the full survey, using all 4 of these techniques in combination to constrain things. So I think the future looks quite bright. The more distant future looks even brighter. People here are leading the charge for the Large Synoptic Survey Telescope, which is on the neighboring Cerro Pachon down in Chile. Bigger telescope, bigger camera, engineered from the start to take advantage of the excellent astronomical conditions at these sites. Will measure, make measurements of billions of galaxies to make many of these same kind of measurements and other ones. When I was down, this is an old photograph from early this year, when I was last down on an observing run for DES, I went over to Cerro Pachon and got a nice tour of the facility. It's much more complete now than even it was then. Very impressive facility going up. So to summarize, the DS is now in its 5th season of observing, planning a half-season extension through the rest of next year. We've put out our results just from our first year, results from additional techniques and from the full survey footprint to come in the next year or so. A lot of ancillary science, only a couple of which I've been able to talk about, are enabled by this. And I want to stress that all these data are being made public. So our raw images become public constraints on this parameter, right? But that's the analysis we've done so far, basically because the data we have so far are not going to give us very tight constraints on this evolving model. This is a constraint on an evolving model where WA is essentially the time derivative of W. WP isn't quite W naught, it's basically W at the pivot redshift, which sort of decorrelates it with measurements of WA. But so this gives you, so you're right, this isn't 4%, but that's because we're now constraining a more complicated 2-parameter model.
It's like 1%.
No, this is, here's 0.95, yeah. So it's it'll be maybe, well, sorry, the constraints on, let me back up. The constraints on WP should be the equivalent to the constraints you would get on W naught in a constant W model. I'm looking to a cosmologist in the audience to nod their head or correct me on that. All right, no one's disagreeing with that, so I'll say it's true. So yes, so this should end up, this constraint on WP should end up being, probably in the order of 2-3%, something like that, I guess, yeah.
Actually, I have a technical question about your decision to look at 4 bands.
5 bands.
I miscounted, 5.
GRIZY, yeah.
5, okay. That was some sort of compromise, and what you'd like is the whole spectrum, and you don't have enough power for that.
We don't have enough time. Yeah.
Right, so, what's next? So after you, suppose you've got this patchy sky, and you've got this data set. Is it worth it to have more bins and measure longer?
Good question. So, yes, both. So LSST is going to cover the same part of the sky we're going to cover. Actually, they're going to cover our part of the sky, and they're going to cover about 15,000 square degrees of extragalactic sky. We're 5,000, but their survey will encompass ours. They're using 6 filters. So U, a U filter, G, R, I, Z, and Y. We also did Y, just didn't have it here. And they're going much deeper than we're going. So they will get, because they're deeper, their photometric redshift precision should be more precise, and they can measure it for more distant galaxies at higher redshifts. Ultimately, what you would want to do, though, to improve this precision even more and get more power out of the data, would be to do one of 2 things. Either build a spectrograph, which can measure simultaneously spectra for many, many thousands of galaxies. So then you would get extremely precise redshifts. So DESI is sort of the next step on that. That's using the 4-meter cousin to this telescope that's at Kitt Peak in Arizona. They're going to measure redshifts for 5,000 galaxies at a time. Riza Wexler here is the co-spokesperson of that project. And they will eventually amass redshifts for 25 million, give or take, galaxies. Ultimately, what we would like to do, the community is now talking about building an even bigger spectroscopic survey in the southern hemisphere that could target all the galaxies from LSST and perhaps measure spectra for hundreds of millions to up to 1 billion galaxies. The nice thing about getting spectroscopic precision on the redshift is that then you can go beyond just a 2-dimensional measurement on the sky. You can now measure all those modes that are in the radial direction as well. DESI will do that, but over a limited volume. What we'd really like to do is do this on an even bigger telescope to get out all those modes that are out there at even higher redshift. An alternative is to do what I think you were suggesting, which is instead of using these 4 or 5 or 6 broadband filters, you can design a system which has many narrow filters. So there are projects which are using, say, 30 very narrow filters, and they essentially get a very rough spectrum out of that, with which gives them higher redshift precision there. That's cheaper than doing spectroscopy, but it has its own technical challenges. And so far, there's really just a couple of, I would say, sort of pilot projects on small to intermediate scale telescopes doing that. But that's a potentially complementary technique to doing this. If we really want to build something very big and ambitious, I think it's going to be spectroscopy, because filters primarily give you, they'll give you a redshift, they'll give you the color of the galaxy, but astronomers really care about all these other properties of galaxies. They want to know details about star formation, histories, and complexities associated with the structure of individual galaxies. And the only way to really do that is to build something that gives you high signal-to-noise spectra. So I think in the future we may go in both directions. But yeah, so an important point is that LSST is going to make an order of magnitude, and DESI will make sort of another order of magnitude leap beyond what we'll be able to do with DES. But there's another order of magnitude beyond those in terms of cosmological information out there in the sky to be exploited for cosmology.
Other questions? Yes?
Your picture of the CCDs had a diagonal line on it. I couldn't get that on
Oh, yeah, it was probably a satellite.
Yeah, the satellite there.
Yeah.
Yeah, that one. Yeah, see those pretty often.
Yeah.
Yeah, sometimes you see airplanes,
Blink.
comets, asteroids. Yep.
Is there one more question maybe? I have actually one. When you look for the electromagnetic counterpart for the Supernova, is the peculiar velocity of the galaxy be a relevant?
Yeah, right. So that's one of the uncertainties in that Hubble parameter determination from that one object, particularly because that event was only at 40 megaparsecs. It's not that far out into the Hubble flow. So the peculiar velocities of the host galaxy and its environment, that's one of the sources, one of the big sources of uncertainty in that Hubble parameter measurement from that one event. Yeah.
Is the long wavelength information that you have there allows you to reconstruct the velocity and really try to...
Right, so in principle you can correct, if we do have information about, neighboring galaxies, you can do a kind of reconstruction of what you think the peculiar velocity field is, but again, there's still uncertainties associated with that.
Okay, if there are no further questions, let's thank